So please sign up if you have not did that before. So please sign up. You only just need to sign up once. If you have already done that before, then you don't need to do that again. Your record will kept in our database. Now, we are also welcome for anyone who are interested in deliver a talk in this online forum. So what you have to do is to go to our official website and then look under this call for presentation subpage. And then down below on this call for presentation, down at the lower right-hand corner. So please fill out this form and send it back to me. And I will assess your proposal. Okay. Now I will have the video recording for this lecture, but subject to the speaker's approval, we will send you the lecture notes and the link of the video recording, usually within 1 week after the presentation. So this is a series of 2 presentations on quantum computing in the financial application. And the first talk is going to present by Professor Kwong Humphrey. He's now a professor associate with the Department of Economics and Finance at the City University of Hong Kong. And the next coming up presentation is by Mrs. Kwong. She's the last year the undergraduate student at the Department of Applied Mathematics at the National Yangming Jiao Tong University, Taiwan. The talk will be delivered, I think, is on December 6th. Okay, Friday, 2 p.m. Okay, so so put this in your agenda, and you're also welcome to join this her presentation. Okay, so I just briefly introduce Professor Humphrey. He received his Bachelor of Degree in Physics from the University of Alberta, and both a Master of Science and PhD in Theoretical Particle Physics from the University of Toronto. In fact, he and me also did our graduate work in Theoretical Particle Physics. And he's a we are a long time friend, okay, since we first met in the academic Seneca many years ago. And he's my good friends for a long time. Although we haven't collaborated on any research work on particle physics before, but it's my honor to know him. Okay, now he was the quantitative analysis of C.ATS, a leading risk management software vendor in the Silicon Valley. He's now an adjunct professor in the Department of Economics and Finance of City University of Hong Kong, and has taught the subject on option pricing and implementation for a master student in financial engineering program since 2003. For that, then let me open the just a minute. Let me
open. You're going to open my PowerPoint.
Yes, just a minute. Let me see. Lecture finance. Okay, let me see. Share and then financial. Okay, this one. Okay, so can you see this, Humphrey?
Yes.
Can you see?
no, page. Oh yeah, yeah. This is
Your
okay.
PowerPoint, right?
Should I
Okay, all
share?
right then. Okay, then let me pass the microphone to you. So I will mute my just a minute. Mute my microphone.
Okay.
Sorry, one more thing. Did you mind we interrupt you and ask question during your presentation?
Can I start now?
Yes, would you mind people interrupt you during your presentation in case we have questions?
Oh, I
Would
can
you?
open up the check box. I don't know how to do that, but just let me start. Okay.
Okay, all right. So maybe someone will interrupt you. Okay,
Yeah, yeah. Because
okay,
sorry for the delay. I'm not quite familiar with Teams, Microsoft. So I have difficulty setting up and also difficulty with the camera and mic. Okay, I'll make it short. Okay, uh, this is the topics. Okay, like few months ago, Professor Ng, talked to me regarding uh, quantum computing on financial derivative pricing. We have some talk at that time, and then recently he want me to deliver this talk, uh, but this talk is not anything on financial computing. Just let you know, um, the I put in this way fundamental ideas of financial derivative pricing. So I'm not going to go through the mathematics, okay, in detail. Just let you know the idea behind pricing, okay, derivative pricing, okay. So and then I'll leave the technical detail to you guys, maybe the expert on financial computing, okay. So next page, next slide, please. Okay, so here derivative pricing, you start off from something called stochastic models. So you have no pay, no, yeah, yeah, you have asset price movement that you see, right? Maybe you see Reuters terminal, like you have like price tick, looks like it moved randomly. So this is what we call the underlying asset price, uh, which you can trade, okay, according to the price that you see in the terminal. But people then invent something called derivative on the top of this price, and then put in actually derivative actually mean a contract among two counterparties, and then some kind of agreement how someone got pay off, and how much you need to pay for holding the contract, etc., etc. So which means derivative mean something derived from asset price movement. So which means the bottom line is you need a model that describe asset price. Okay. So then people think about like asset price should move like very random. So they put on define something called stochastic model. So which means a random model that describe asset price movement. Okay. So which means suppose you see like in bullet one, you see asset price like from last September, okay. One of the asset here, okay, it just like daily changes you can see, and then people try to describe, okay. Otherwise, nothing you can do. So you need to put in a model that you believe you can describe this kind of movement, but still it follows some kind of like random process. But how random, according to what parameters, then there's something called stochastic model in bullet two. Okay, so bullet two, price return is a random normal number. So this is stochastic model. So it follow random normal distribution, and then it got some mean and also some standard deviation. And and then so like in bullet two you have like let's say you have like a time increment. I put in like delta t. So let's say day by day, okay, time 1 day time increment. So which means yesterday compared with today, and then you work out a fraction, then you believe it follow or it behave like a random normal process, or we call that random normal number. Okay, and there will be parameters, say like the first one, mu. Okay, usually call that mean, and sigma you call that volatility. And the fact that mu multiplied by delta t simply refer to you can have mean simply scale like how many days. Okay, so which means mu and sigma simply mean the parameters. Let's say there's a reference time, let's say per years, let's say 20% per years or whatever, and then delta t will be how many years. Okay, so which means 1 day, then 1 over 365 years. Okay, so in this stochastic model, there will be parameters. Okay, mu and sigma, for example, and it can be constant or whatever you want. Okay, so depending on whether you think about that seriously or not, uh, simplest thing to do is you can put them to be like constant. Okay, so but constant in in what values. Okay, so so models parameters of stochastic model, there's something called calibration. So which means everything you need to go back what you see in the market. So your mean and sigma parameter also need to respect what you see in the market. Okay, so we call that calibration. And in fact, this is difficult part in derivative pricing. You think about the two parameters are constant, then you can simply look up your history and then try to work out the average. Okay, or this actually mean the average price return, let's say last 10 years. Sigma maybe like called as standard deviation for historical price return, let's say last 5 years. No, go back to that page. That page. Yeah. And there are a lot of things to tell for these two parameters. Okay, so but just remind you, you cannot simply put in like two number for mu and sigma. We need to calibrate according to the market. Okay, so now suppose you have a model on you search your stochastic model, and then you have some idea how to model mean and volatilities. Then you move on to, let's say you have a derivative contract on the top of this asset price. Okay, so now you need to think about how do you actually price this contract. Okay, so we call that in bullet for derivative pricing. Um, so there's a very famous theorem called Black-Scholes pricing theorem. Okay, next page. So first, what is a derivative contract? Okay, or what is a derivative? Okay, it's actually so you have like buyers and sellers. Okay, so which means you have one what we call the underlying asset. Okay, it just you look at Reuters terminal and then you see that the asset like change like day by day or minute by minute. Then you have two party, one side called buyer, someone want to buy a contract from you, and then you are the seller. Okay, so and then you two sit down and then make agreement. Okay, so which means you write down detail. The buyers should got some kind of like requirement. Otherwise, he or she don't want to buy a contract. Okay, so a buyer put down detail how I want to pay off because this contract. Well, first this contract will expire. Okay, so you're going to lay down this contract today, but this contract will last for let's say 1 year. Okay, 1 year later on, then you think about how I got paid off from this contract. Okay, so there's a maturity time, let's say call that T. So make it simple. What happens 1 year later on? Usually it will depends on the asset price. So which means in bullet one, if you look at the contract, okay, I don't know whether you can see the mouse. this is the price, okay? You don't know this price. Let's say 1 year later, this price will be random, and you believe it follow the stochastic models. So, but you still don't know what this price is going to be 1 year later on. So this contract is betting on this price 1 year later on, and the buyers and the sellers like sit down and then discuss the detail of this contract, how buyers got paid off according to this price. Buyer should have his own reason why he won this contract, and seller simply need to respond. And then the most important thing is for the seller is if if I sell you this contract, I need you to pay me an amount. Okay, so this is what we call the contract price. So which means at the very beginning, they agree upon the detail here, how this financial derivative contract looks like, and then seller figure out what this price gonna be. Otherwise, why the seller want to sell this contract? Okay, so this is what we call the derivative price. Okay, simply the contract price. Okay, so if you look at bullet two, okay, bullet two, you're sitting at here. Okay, you're sitting at, so let's say 0 time currently. Okay, at current time, and then what you don't know is the movement of the underlying asset. Okay, we have stochastic model. So suppose for some kind of scenario, okay, suppose it looks like this for the following, let's say this is like 1 year, okay, and then end up with a price like that. Okay, so we call that maturity or expiration price of the underlying. Okay, so we want to, in particular, the seller want to figure out the price of this contract. So in terms of mathematical model, it's actually according to the model, okay, option pricing model. Um, this contract in particular at current time, if you know the current price of the underlying asset, okay, at current time, 0 time. So this is what we call, so there will be a formula, okay, uh, uh, which you plug in t equals 0 current time, and then you plug in current price, and that will give you current value of this contract. So which means the seller will agree to sign this contract. So which means once the seller signs this contract, he or she is liable to all the detail in the contract. Okay, so but he need to receive an amount from the buyers, which is the price. And in derivative pricing model, there will be a formula, okay, according to current price and at current time, and then you can calculate what is the price. Okay, um, and and um, how we actually figure out this formula, okay, and also there's a meaning, okay, in particular, more importantly, the meaning, why the seller think about this price here will be the correct price that he should receive. And then because once he received this amount, okay, you think about, like, if it happens to be like that in bullet two, the current price, random walk, like the red color path, okay, and then you have a formula, okay. The formula for the option price, it can apply at current time with 0 time and current price. It can also apply to any time during the life of the option, okay. So which means during the life of the option, if you put in t, okay, at which time, and also at which price. So during the live, underlying will just like random walk, okay? And for any particular instant, you can take down the time, and you can also take down the asset price, and then you plug into the formula, and that will also give you a price, okay? And this price is what we call the forward price, representing, if it happens to be at that time you see this price, the option will follow the option price to also to follow the formula. So which means that's why I have that the blue path. Okay. So if the underlying asset undergo the red path, then the green one will be the formula. Okay. And in particular, at maturities, when underlying is S with big T, then you plug in maturity time and you plug in the underlying asset price at maturity, then this is exactly the payoff. Okay, so which means this payoff. So which means in the sense that the buyer and holder of the contract simply sell back the option contract to the seller and then receive the amount, we call that payoff. Okay, so and there's a reason. Okay, I think I mean the fundamental idea simply refer to the reason why this contract price makes sense. Okay, if both sides see uncertainty, because like the underlying asset will undergo random walk, okay, and presumably there's a function evaluate according to what you see regarding underlying asset price, it also random walk. Then if both parties see uncertainty, why this price actually makes sense, in particular to the seller. Okay, next slide, please. Next slide. Okay, it just referred to there's something called stochastic calculus. Okay, um, if you believe in stochastic model, then let's say you have an option function. Okay, uh, um, we don't know the function yet, but suppose there's a function that describes the option price. Okay, and then if you think about like so which means at any time t you evaluate based on what you see regarding the underlying asset price, then plug into the formula, then you got a value, which we call that option price at that particular instant. Now, but we know, okay, both underlying asset and the option price undergo random walk, so uncertain. Okay, we don't know what happens because we have like stochastic process. Underlying asset price undergo random movement, and it will lead to the option price also undergo random movement. Okay, so here there's a very important theorem called Ito's lemma. Okay, uh, which tell us how to extend regular calculus into what we call stochastic calculus. Stochastic calculus simply means you have calculus, but on the top you will have, let's say in bullet 2, okay? In bullet 2, we have a stochastic model. And the first term, you can think about that referring to regular calculus. But the second term, there's a random normal number, okay? And so stochastic calculus simply let us do the thing called calculus, but on the top you want a random number that involved in the calculation. Okay, because like stochastic model, this is the term in red refer to a random normal number. Okay, so um, so let's say Ito's lemma simply one very important theorem regarding if you have stochastic calculus. Okay, very important properties. So let's say I look at the option function at any time t, and then let's say if I move forward a tiny time, let's say called delta t. Okay, and we know the change of this option function will be random because you have random process involved for the underlying. You have like for regular calculus, okay? Uh, um, uh, you can work out like let's say in bullet 1 how an option function change going from t to 1 delta t, a tiny time increment later on. So we have the increment of the option function, and then you have the partial derivative with respect to the price and also with respect to time, and then for regular usually if we're doing calculus, we just stay there, and then because the next order will be in the square. Okay. Usually in differential limit, we don't care. Okay. We just need to retain the leading increment. But it's still there. Okay. Only when we go differential time, then we don't have second order term. So which means plus order in second power. Okay. In time and in price. And then So everything go back to the stochastic model of the underlying asset, and in particular the term in red, okay, for bullet 2. So which means if you plug in going from T to 1 delta T later on, how underlying asset price random walk, in particular, there's a term in red representing a random movement. Then you pull it back and try to see what happens to the option function. Then so far it's okay. Okay, you can work that out according to regular calculus. But regular calculus do not give you the term in bullet 2. There's a term which refer to one half sigma square s square. Okay, second derivative of option function with respect to price. I suppose you see this term. Uh, 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 this term, okay, in regular calculus, okay, you don't see this term. Okay, because in stochastic calculus, because in the stochastic model for the underlying asset price, price change, okay, with a square power, okay, and so imagine you take square on the stochastic model of delta s, okay. uh, um, you will have like first order in time and then second order in time, and second order in time usually you ignore, okay, when you take differential limit. But when you look at the random term, because of random normal process, behavior of random normal process, the standard deviation will have a square root of the time increment. Okay, so this is like the square root of time increment according to, you're talking about a random normal number. Okay, so if you put in a square, then this square root time increment now with a square, then you have the same order like your leading behavior. Okay, so which means Ito's lemma simply tell us how to retain, like in my bullet 1, the term in green, okay, in green, actually contribute to the change in option price, okay, and it will lead to an additional term you don't see in regular calculus, okay. So this is so if you have underlying, if you have the asset random walk, option price also random walk, okay. Now, what makes sense, okay, regarding the option price at current time will be something called the delta hedging. Uh, 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 you, 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 you can actually uh, uh, let me go back to one page back, okay. Um, so the price, okay, the price that seller receive, okay, the is the seller don't simply receive the price and then sit there and do nothing at all and then wait until the option mature and try to see what it got, okay, what he or she got at the end, okay. Um, this price makes sense according to what we call delta hedging of risk. One slide back, one slide down, okay. So you can compare, okay. In bullet two, if you compare stochastic model, okay, the two term in red, okay, the two term in red. So which means if underlying asset price random walk one step, okay, there's a random term in red, okay, and the corresponding movement, random movement for the option price after one step, also there's also the term in red. You can see these two terms actually, in terms of random number, okay, these two terms get the same random number, but the coefficient or those coefficients that attach to the random number simply being different. But the random process are the same for underlying asset price and the option price or option function. So if you think about like in going from T to 1 delta T later on, okay, if you try to construct a portfolio, okay, in bullet 3, there's something called delta. Delta simply means the partial derivative option function with respect to the price. So you can see in bullet 2, I put it in gray color, right? In gray color, okay? So if I sell one option, okay, for the seller, if I sell one option and then I buy delta underlying, okay, then what change, what I got, what the random change of the underlying asset exactly cancel out, okay, with the random change of the option price, okay. If I have the delta according to the partial derivative in gray color, okay. But of course, like there are also, if we are talking about like finite increment, okay. So so let's say my time change being finite, okay. Before we go differential time, okay. Um, um, uh, there will be a correction term, okay. You can see in my bullet 2, the correction term also in some order of the time increment. So let's say delta t being, let's say 1 minute. Okay, every 1 minute you are going to delta hedge your derivative. So you sell one derivative, and then you are going to buy delta underlying in order to cancel out the risk for one minute later on. Okay, so which means so your the uncertainty according to the correction in the orders uh, in bullet 2, um, um, you only if you go differential time, okay, then so which means that's why later on you will see a differential equation that tells you what this option function looks like. And if you go differential time, then this what we call there's a name called delta hedging portfolio. Minus one option, you always minus one option for a seller, plus whatever you got for the delta. So delta is a ratio which for the risk term in option price and underlying asset price. If you figure out the right delta and then formulate this portfolio, you can always cancel out the uncertainty. When you have your time increment getting smaller and smaller, then your uncertainty will get smaller and smaller. Okay, so go one page down. Okay, and I'll show you. Um, so which means so you have like the ideas of the option price at current time actually mean uh, um, so seller receive, like in bullet 1, seller receive this amount. Option price, option formula at current time, evaluate at current price. Okay, and then at maturity, there will be a payoff that defined in the contract. Okay, so which means at 0 time, immediately right after the seller sell the option and receive the amount. Okay, and then there will be the seller will immediately formulate a delta hedging portfolio. Okay, and this portfolio, let's say he need to selling one option in bullet 3. The portfolio value refer to like selling one option. Okay, he received option price, but he need to buy delta underlying according to current underlying asset price. There's there will be also I'm not going into detail. So to formulate this delta hedging portfolio, you need to save or borrow from bank, okay, to make it what we call self-financing. So which means the seller need to keep on doing that. Okay, so let's say minute by minute or hour by hour, the seller need to rebalance because the underlying asset price will keep on changing. Okay, so keep on what we call review or renew, rebalance. Okay, rebalance the delta. Every time there will be a portfolio, delta hedging portfolio, which require the seller to borrow money or sometimes got some saving. Okay, the idea will be if the seller keep on doing that, okay, what happens at the end? Okay, um, the 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 seller during the time, the seller, the portfolio itself during the time of the rebalancing period always being zero. Okay, because simply you take into account option, asset price, and then the bank, and then we call that self-financing. So which means the three add up to zero. The three add up to zero. Okay, uh, one delta t at a time, always being zero. Okay, so now at the end, okay, if the seller keep on doing that, okay, at the end, okay, by the time the option mature, the seller will settle with the buyers. Okay, you can see in my bullet 5, you have like the portfolio, we call it delta hedging portfolio at current time being zero. One delta t, you can make it zero by borrowing or saving, and all the way to the end. Okay, what I put in portfolio at maturity V capital T equals what? Okay, at that time you cannot like borrow and save. Okay, you need to settle with the buyers. So which means there will be profit and loss of selling this contract. Okay, so next slide, next slide, next slide. Okay, here I put in this is a simulation game. Okay, just try to illustrate what does it mean. Uh, um, so uh, uh, let's say for example 1 year's maturities. Okay, so you can make it like you can here the first plot will be, let's say the seller only rebalance 10 times. Okay, so 10 times. Okay, then at the end the seller cannot make the portfolio settlement value being it will be random. Okay, actually highly risky. You can see I simulate this. I simulate like 10,000 scenario. Okay, every scenario there will be a maturity value uh, the profit and loss of the seller, and then you can see it will be uncertain. Okay, highly uncertain. Okay, and then next plot will be for times rebalancing 100 times. Okay, then you start seeing the profit and loss of the seller now being less certain. Okay, you can see I can compare the variation of the profit and loss. Okay, and then the third one, let's say 1,000 times, then even less uncertain. So which means if you have the time increment go differential time, okay, and then which means you're going to look at tick by tick, differential time by differential time of the underlying asset price, and then delta hash according to differential time. You will have the profit and loss of the seller being, you can see the middle will be zero. So which means profit and loss of the seller will be zero. Okay, but he is taking no risk. Okay, so what's the point of selling the option? I think this is the point. So the price of the option, okay, so the seller receive option price, and then this option price only makes sense if he or she follow a delta hedging scheme, and also need to be continuously rebalancing. Okay, otherwise he or she need to take risk at the end based on some kind of uncertainty of for profit and loss. If he or she do that continuously, okay, then for sure he got nothing. So he received option price, and also based on the option price, allow him to start off delta hedging scheme, and then at the end, if he calculate profit and loss at the end, if he or she do that continuously, then at the end of the day, he got nothing, but taking no risk. You can see nothing and taking no risk actually take into account something called in finance or economics, very important principle, no arbitrage principle. How much time do I get more? Okay, next slide.
You can, yeah,
Next slide.
yeah, keep yeah, presenting. Maybe
Next slide.
you need another 10 or 15 minutes. Is that okay? 10 to 15 minutes.
Can you go down? Go down one slide.
Okay.
So I think I'll make it quick. Okay. So which mean this is the ideas. Okay. Um, so which mean which mean uh, there's a differential equation called Black-Scholes differential equation that allow us to have to calculate to derive the pricing formula of a derivative. It's simply the same kind of argument, okay? And uh, if option function satisfy what we have mentioned earlier, okay, and if so, which means if option pricing function after rebalancing and then after receive certain amount at the very beginning and then continues the hedge, and then there will be no risk at the end, and also no profit and loss at the end. So which means you simply follow the same kind of argument. So I don't have time right now. Just let you, if you follow the same kind of argument, and then you look at, for instance, in particular from t to 1/3 t, one differential time later on, and then put in the same argument. In particular, more importantly, the no arbitrage principle. Okay, so you will have a differential equation. We call that Black-Scholes differential equation. Okay, so bullet 4 is what we call Black-Scholes differential equation, and this equation is universal. Okay, but you need to include, we call that boundary conditions. Boundary conditions simply mean how this can pay off, or whether you have some kind of like external requirement. Let's say American option, maybe you can heard about that. Uh, I have an option that allowed me to claim for the payoff anytime if I want. Then it will be boundary condition. So which means the differential equation itself, it will be universally true for different options, and different option will have different formula according to when you solve this differential equation according to some kind of like boundary. Okay, so which means option pricing now becomes a boundary value problem. Okay, so this will go back to maybe advanced calculus. Okay, uh, one slide down, one slide. And I mean, like I can quickly go through how do you actually solve this. There's something you're going to use. You can the common method will be finite different. Maybe there's a more method. Uh, Usually we don't know how to solve the differential equation analytically, so there will be numerical procedures. I think this is what you guys like working on financial computing more interesting on. There's the most common scheme called Clay-Nicholson. So you are going to have like discrete price and time, and then you are going to approximate the derivative inside the differential equation, and then you end up with a matrix equation. So you can see I have like two column matrix, right? Actually, left-hand side at time t of I, and then under with different price, we have discrete price, okay, and also discrete time. So what happens at ti for different price, and then it can relate it to what happens at ti plus 1 for the same set of prices. And then, of course, there will be a matrix, okay? This will be a matrix operation, and you are going to, in particular for option, you start off with, because the option, in option contract, you know how this option got paid off. So which means you know what happens at payoff, and then usually you're interested into what happens at current time, what is the option price at current time, which means you start off from maturity based on how this option got paid off, and then you backward iterate. We call that backward induction. Okay, and the difficulty will be the dimension of this of the two matrix. These two matrices are bullet 2 matrix U and matrix P square matrix, but the size being tremendous, depending on how many discrete price that you want. Okay, and so might not be that efficient. Uh, it will be very slow. Okay. Also, in particular, if you have boundary conditions like American option, because by the time you solve this matrix equation, you also need to take into account boundary condition. Okay, so might be very heavy duty if you have your number of prices being very large. Next page, next page. Okay, next slide. Um, there's also another method. The previous one, solving differential equation, you can do that based on differencing. Okay, finite differencing. There's also another one referring to you might heard about like Monte Carlo pricing. Okay, it's actually called risk. Is pricing an alternative way to implement Black-Scholes differential equation, but in terms of probabilities. Okay, um, in bullet one, the idea is bullet one, you define something called previously we have stochastic model that describe the underlying asset price, but in this pricing scheme, you are going to make the mean term. You can see bullet one, the mean term being R delta T, and the random term being the same like in stochastic model. This is by definition no meaning in the market. By definition, it makes the following probability interpretation of the differential equation being true. Okay, so define something called risk neutral process, not quite the original stochastic model of the underlying asset process, because you already make changes on the mean term. R actually mean interest rate. Okay, and then um the 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 consequence. Okay, so now if you tune into if you look at not you don't if you look at this neutral process rather than the stochastic model of the underlying, you have an option pricing function. Okay, now the idea is if you use the same option pricing function but evaluate based on the risk neutral process. Okay, and then you can argue that. Okay, uh, um, well, of course, like I suppose I have the option pricing function. I want to figure out option price. Of course, I need to evaluate this option pricing function according to what? To real underlying asset price, the price that I see in the market. But this pricing technique, if you evaluate according to this risk neutral process by definition, there will be very nice properties because when option pricing function evaluate based on the risk neutral process, uh, how it change is according to a martingale. What does it mean by a martingale? Well, of course, like so here, if I evaluate this option pricing function according to risk neutral process, and then if I put in a discount, so which means we call that net present value of option pricing function evaluated according to risk neutral process, and it actually follow a martingale. Okay, martingale means you don't have any mean term. You just have random term. Why this is so good? Because in in probability theory, if something behaves like a martingale, you can relate. So my bullet three, properties of martingale. Okay, in particular for my option pricing formula. My option pricing formula, I know discount of option pricing formula evaluated according to risk neutral price behave like martingale, and it got these properties. I can have two types. Okay, on the left hand side, bullet three, left hand side, if I do that at time t for risk neutral price at t, okay, it is the same as right hand side anytime s after t with the discount if you work out the average. Okay, so which means So which means what you see at time t, okay, regarding the risk neutral underlying asset price, and then if you let it random walk and then work out, because everything will be random, even because this is also a random process. Later on, at later time, as if you work out this same quantity but work out the average, it will be exactly what you see at the time. So which means at time t you see q of t, okay, and then this is what you see today, okay, at time t. This is what you see inside the expectation, is what you see later on, okay. So you work out the average, it will be what you see, exactly what you see at time t. This is a very nice property because for option pricing, you can think about inside the expectation. You can put in what you expect at payoff, okay, because you have a payoff function. So which means you just need to define the payoff inside the option contract, how it looks like, and then work out the average, and that will tell you what you expect at time t, uh, conditional to what you see regarding the risk neutral asset price. But this is always a risk neutral asset price. But why this is useful? You think about this in an alternative way, okay? And because you have this function that you want to evaluate, okay? Suppose numerically, and this bullet three, you put in what happens to risk neutral asset price. But if you have the risk neutral asset price exactly like the asset price, real asset price, okay. So numerically, since you have the same function, you just evaluate according to asset price or risk neutral asset price. It's up to you. But if you make the two being the same, then numerically, bullet four option price will be exactly what you want. If you want to evaluate the option price based on what you see regarding the real market underlying asset price. Okay, so this is an alternative way, and it will be equivalent. You can prove that this pricing formula is equivalent to the pricing formula according to the Black-Scholes differential equation. So numerically, there will be Monte Carlo simulation because you can always simulate, okay? Because you can always take these procedures and then simulate out, let's say, 10,000 sample and then work out the average. So this is what we call the Monte Carlo pricing. And you can also redefine expectation based on a tree, okay? So there will be binomial tree, trinomial tree, or finite difference tree if you want, okay? So one page down. Okay, let me finish this. I think. Um, I think I have the ideas for option pricing. Just why you might need to think about when you solve pricing formula, uh, um, you might need to use quantum computing or whatever, okay, because it will be very heavy duty, okay. Um, Depending on whether you want that to be consistent with what you see in the market, okay? Because in the market, you see asset price, you also see option price being traded, okay? So which means your option pricing formula at least being consistent with market option price, okay? So it will go into the volatility, okay? Uh, um, so there will be volatility model and not simply constant, okay? It can be a function, volatility function. And so there will be a lot of work in terms of how you calibrate. So you have a model, but you also need your model consistent with the market. So you need to calibrate with market prices. Okay. So this is one tricky point. It will be like very heavy duty. Another point will be interest rate. So far, the ideas that I have shown you take interest rate to be like constant. Okay. But uh, of course, interest rate is not constant. So discount, so let's say put it to discount factor, if constant interest rate is just like E to the power minus RS. But actually, you can have bond price, okay, bond price in the market random walk. If you take bond price and then transfer bond price into interest rate, you can see interest rate also random walk. So which means discount factor according to random interest rate model. Okay, you can see the integral. Okay, right-hand side of the arrow, integral referred to when you have interest rate also random walk, and then you have pure interest according to integral, then it will be what we call integral factors. Okay, and more importantly, is path dependent. So which means how this interest rate random walk like a path, and then you are going to pure interest rate. Okay, so which means you also have stochastic model for interest rate. Okay, and uh, um, that will be the difficult part, because like contemporary interest rate model being very, very, very complex. Okay, because you don't know how, it's not simple. It's very difficult to figure out drift term and volatility term of interest rate. Okay, so the mu out, sigma out, because interest rate got a lot of like, I keep on saying like calibration, because you cannot simply put in whatever you want. What you put in need to be consistent with the market. In contemporary interest rate model, drift term and volatility term follow a lot of like ideas. Let's say the no arbitrage, and also like you can have, sometimes you might need to have the volatility being stochastic as well. Okay. Um, so the final risk neutral pricing. Okay. Let me show you the formula. This is like risk neutral pricing that I've shown you earlier. But if I also have interest rate being random stochastic, then this is discount factors. And also this is like the option price. So, like let's say you have a stock asset within, you have an option within on stocks, but interest rate also random walk. Then how you price this option need to take into account random asset price movement and also random interest rate movement, and then try to figure out under risk neutral pricing, try to figure out the risk neutral average. If you go back to differential equation, then the equation that I've shown you earlier might not be correct. Here, if you have two random processes, then fractional differential equation, the previous one need to include term like uh, uh, these three. Okay, the terms with like the derivative with respect to interest rate, and also one time, two time, and also the correlation between random asset price and random interest rate. The last one. Okay, I think that's I want to say today. Sorry for the delay and taking you all the time over time. Okay. Okay, I'm done.
Okay, thank you. Okay, thank you, Humphrey, for
If you want,
the very detailed presentation.
your
Okay,
question.
okay, all right.
I can.
Yes, so I think we are welcome for people
I cannot hear.
Hey, can you hear me? Can you hear me? Yes, can you hear me? Hello?
Yes, Prof.
Yes. Humphrey, can you hear me? Can you hear me, Humphrey? Looks like you cannot hear. I am speaking. You cannot hear. Right? You cannot hear. You need a headphone, or you need a headphone or not?
Oh, I see.
Yes. Okay.
Okay, give me the idea.
Yeah. Can you hear me now?
Give me some time.
Yes.
I need to turn on the audio here.
Okay. Okay. All right. Yes, I think we can wait for a couple, maybe a few more minutes. The speaker need to
I'm using a
tune up.
teaching either, so I need to turn on
Okay.
the higher audio for the
Okay.
room
All right.
first.
Okay. Okay. All right. I can hear you.
Okay, I can hear right now.
Okay, you can hear me now, right?
Yeah.
Okay. 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 Now, thank you, Humphrey, for the very technical presentation about the Black-Scholes equation. So now I think we have time for the audience to raise a question about Professor Tung's talk. Okay. You can open your microphone or you can type your question in the chat box. Yes. Not sure. Okay.
Maybe I'm going that too fast. Okay,
Okay, then maybe let me pose a few questions first. When you talk about the ideal lemma, you have a stochastic term, square root delta t times epsilon. Is it that has to be the Brownian motion or
right,
it's not?
yeah. That's the Brownian. They call that Brownian motion. But it's actually a random normal process.
Uh-huh.
Square root delta t because it's a random normal. So variance add up standard deviation. You need a square root.
Okay, I see. All right, but one can use other process other than Brownian the motion, right?
Sorry, say again.
I mean, one can use other stochastic process instead of Brownian model. Other.
You need to be careful. The entire argument for the delta hedging only work for random normal, because other process you might not be able to cancel out the high order term.
Okay.
So I think somebody tried doing that, but I don't know the result of that for them.
Okay, I see. Okay, all right. And then another question is about you in your slide the value of mu and sigma. It has to match the current marketing value, right? The mu and sigma. It has to.
Yeah. That's the another topics on calibration. Usually, you can make it constant. Okay, mu and sigma. Mu actually doesn't really matters, except you go interest rate model. Okay, sigma are critical. You cannot simply put in like whatever you want. Okay, because in the market you can have like option also being traded. Okay, in the market you have option price. Okay, so your model, your mu and sigma, will give you a formula. Your formula include these two parameters, and then for those options that you can trade in the market or you can see the price, your formula need to at least consistent with the market prices. Okay, we call that calibration.
Yes.
All the time, if you put in constant, let's say in the market you have call option and put option, if you put in constant sigma, okay, you can only match one part of the call option, another part. Usually you cannot do that. That's why there's a term they call that volatility smile. Okay, volatility smile simply means your volatility cannot simply be like a constant value. It at least looks like a curve, like how we smile curve. Okay, like that. So you want to make it easy, then you put in constant, and then you can work out formula or numerically, analytically. But if you want to in line with what you see in the market, then that will be you need quite a lot of work on, in particular, how you model the volatilities in particular. Okay, usually volatility model being play an important role. Okay.
Okay. A follow-up question is, recently we are always talk about AI and machine learning algorithm. So, are you aware of any work that people applying machine learning regression or parameter estimation methods to model mu and sigma?
If you want, you can try to learn all this from data.
Yeah.
But as I say, um, you might not be able to satisfy everything.
Okay.
If you simply do data mining, but if you are very keen on the theoretical issues, then you don't do data mining. But the market, actually, the market price actually doesn't care too much about the theory. Okay, that's why people invent a lot of things. Let's say there's one method about that implied volatility. So which means uh, uh, I have the market price not quite the same as what I on the theory. So I can tune them to be the same based on something called implied volatilities. Okay, so if you want, so what I mean is market prices not quite follow the theory all the time. Okay, so if you don't care about like all the like ideas regarding the theory, then you can always go data mining. Okay, because at the end of the day, you have a price. If that price somebody willing to take, then it's over. It's okay. Okay, but that price, the price that you see somebody trade that price, but that price might be totally violate the theory. You don't know, okay? Because the market don't really cares sometimes, okay? But for academics, then we have all these three behind the market prices. So you can try like doing like AI on that, okay? As I mentioned to you earlier, I think like last month, um, uh, uh, people already data mine because like I mentioned in the talks, there's a delta. Okay, uh, um, people also worry about how because like in practice you cannot have delta in a continuous way. Okay, so which means you might need to have some other benchmark, maybe some other reference. They call that Wenger. Okay, people try to figure out Wenger. Wenger simply tells you how fast delta will change. Okay, later on. So people try to figure out Wenger from data, and then try to have some ideas. Once I know have some ideas on Wenger, then I know how delta will change in the next moment. It's so deep, then I will take another delta. If not quite deep, then I can simply sit there and wait. Okay. So there's one part I heard about like uh, uh, um, you learn Wenger from data, okay, or machine learning of Wenger. Other than that, I heard that from you. You told me before all this. Okay.
Oh, okay. Yes. Uh, Another question is you talk about this P and U matrix, right? Can you see?
Oh, I haven't put in the detail.
Yeah.
If you follow the calculation on the left hand side, okay, I try to approximate partial derivative. Then you plug back into the equation, okay, plug back into fractional differential equation, and then organize a little bit. Then you will have P and U matrix work out. I haven't define PNU, but just that you know there are matrix called PNU in square matrix in this dimension, and actually you can work that out very easily. Just take the approximation on positive derivative back into the equation, then you can easily extract out PNU.
Okay, okay. Now, is the PNU matrix, they are tri-diagonal. Are they also sparsy or not? Do they have a lot of a number of
That
zeros?
part I don't know whether it's sparse or not. I don't know, but
Okay.
definitely invertible. Okay, definitely invertible.
Okay. Oh, okay. Yeah, because I know in the quantum computing, there's some algorithm, the so-called HHL algorithm, which is good in finding the inverse of a matrix. Yeah.
You can try. As I talked to you before, I can show you how UNP looks like. Okay, and actually, it's actually not quite complex, but
I see.
it complex in the way that it also depends on volatility. So, which means if you have models on volatility, then you need to update. Okay, when you iterate,
Okay.
when you backward iterate, you also need to update volatility, and that
Okay.
will be so, which means your volatility also need to calibrate with the market. So there will be a lot of work before you can write down UNP and then iterate one step, and then you need to do that one more time. So I think the difficult part is not how you invert, okay? It's how you construct PNU in the first place.
Oh,
Okay.
I see. Okay. All right. Okay. Thank you for your
Sorry
answer.
for the delay.
And are there any other questions from the audience? Yes. Any other questions from the audience? Okay. So if not, then I can close this presentation.
Okay. Bye bye.
Okay. All right. Bye bye. Bye everyone.